Dear students, welcome back to NPTEL online certification course on analog electronic circuits. Myself Pradeep Mandal from E&EC department of IIT Kharagpur. So, today we are going to continue the discussion on common collector and common drain amplifiers. So, the outline of today's presentation, it is given in the next slide. What we are going to do today, it is primarily we will be focusing on numerical examples and design guidelines of common collector and common drain amplifiers. So, I should say whatever the knowledge we have gathered in our previous discussion, namely the analysis of voltage gain, impedance and capacitance of common collector and common drain circuit for ideal situation, as well as considering the different parasitics, namely source resistance, load resistance and collector or drain terminal resistances, that will also be getting utilized in the numerical examples. So, let us start with one numerical examples where we do have idealistic bias. So, we do have the common collector amplifier given here, and then we do have the bias circuits, it is given here. In fact, I should say that VBB it is given. Yeah. So, we do have the VBB, it is making a bias at the base terminal, and then we do have the DC supply of 10 volt. So, VBB it is given here, it is 6 volt, and then we assume that the thermal equivalent voltage it is 26 millivolt. Then we are also considering that load capacitance connected at the output node CL, and its value it is say 100 picofarad. So, these are the situation, load situation, and then the device parameters are given here, namely the VBE on it is 0.6 volt, beta of the transistor it is 100, early voltage it is a 50 volt, and then the parasitic capacitances, namely the C pi it is 10 picofarad, C mu base to collector terminal C mu it is 5 picofarad. Now, what we need to do it is as we have discussed earlier, the important parameters are the voltage gain, and we are expecting this voltage gain it will be as small as possible, or rather I should say attenuation is as small as possible. So, the voltage gain we are expecting it will be close to 1, input impedance should be as high as possible, output impedance should be as small as possible, input capacitance also should be as small as possible, and then based on the output impedance and the load capacitance we can find what is the upper cutoff frequency of the frequency response. So, these are the things we need to find, these are the final performance matrices, but the intermediate steps are we need to find the operating point of the transistor or the circuit, and then small signal parameters values, namely GM and GD of the transistor. So, let me start going to the operating point first. So, if I analyze this circuit and if I consider bias current it is 0.5 milliampere it is given to us. So, we can say that the collector current it is also approximately equal to the emitter current. So, that is 0.5 milliampere. Then the base current, quiescent current it is IC divided by the beta. So, that is 500 divided by 100 microampere. So, 5 microampere. Then the VBE it is given to us. So, VBE it is approximately 0.6. Now, we do have the current is flowing through this transistor, and we do have 6 volt at the DC coming to the terminal here. So, if I consider drop across this resistance RS, that gives us the base voltage. Now, for this case, let you consider the source resistance is very small. So, we can say that the base terminal it is also equals to 6 volt, because the source resistance it is 0, and then the emitter voltage it is the 6 volt, the base voltage minus VBE on. So, that is we do have the 6 volt minus 0.6. So, the emitter voltage it is 5.4 volt. On the other hand, the collector voltage anyway it is 10 volt VDD. So, we can say that VCE equals to 10 volt at the collector minus the emitter voltage, which is 5.4 volt. So, this is 6.6 volt. So, from this one we can say that the transistor it is in active region of operation. So, that gives us the operating point of the transistor. Now, let us look into the small signal parameters values, namely GM and then R pi and then the RDS, or rather in this case it is not RDS, rather R naught, collector to emitter terminal resistance. So, let me go one by one. Small signal parameter, values of small signal parameter. Let me start with GM, and you may recall its expression in terms of the quiescent current. It is collector current divided by thermal equivalent voltage, and collector current it is 0.5 milliampere divided by 26 millivolt. So, we can say that this is 1 by 52 mho or ampere per volt. And then R pi, the base to emitter impedance R pi. So, that is, you may recall that this is beta divided by GM. So, it becomes 100 beta multiplied by 1 by GM, it is 52 ohms. So, this multiplied by 52 ohms. So, that gives us the value of 5.2 kilo ohms. On the other hand, the collector to emitter terminal resistance R naught, which is early voltage VA divided by IC. Now, early voltage it is given us here, it is 50 volt divided by 0.5 milliampere. So, that is equal to 100 kilo ohms. So, now we obtain the small signal parameters. So, you can recall these numbers. So, we are going to utilize the same space to calculate the voltage gain, and then input impedance, output impedance, and so on. So, let me clear the space, and then again let me start with the voltage gain, small signal voltage gain AV equals to VO divided by V in. If I say that small signal voltage here it is VO, and the voltage coming here, it is V in. So, for small signal, of course, this terminal it will be AC ground. So, we may say that this is connected to AC ground. Now, the expression of the voltage gain you may recall for this circuit, it is GM into R naught plus 1 in the numerator, and then in the denominator we do have GM R naught plus 1 into R pi plus R pi, right. And just now we have discussed about GM into R naught. So, GM it is 1 by 52, and then R naught it is 100 K, right. So, 100 into 10 to the power 3 plus 1, and in the denominator we will be having this GM into R naught. So, that is equal to whatever 10 to the power 5 divided by 52 plus 1 multiplied by R pi, that is 5.2 kilo ohms, plus this yeah, I think this is this should be R pi and this is R naught. Anyway, yeah. So, let me write this values of this GM into R naught, which is 10 to the power 5 divided by the let me clear it. The voltage gain, it is AV equals to GM into R pi plus 1 into R naught divided by GM into R pi plus 1 into R naught plus R pi. The other form, it was having some anyway, this is the correct one. So, now GM into R pi equals to beta plus 1 into R naught, and in the denominator we do have beta plus 1 into R naught plus this R pi. So, in the numerator we do have beta is 100. So, I should say, and then R naught, it is what we said is 100 K. So, 101 into 100 K 10 to the power 5 divided by 101 into 10 to the power 5 plus 5.2 K 10 to the power 3. So, naturally you can drop this part, and then you may say that this is approximately 1. So, that is what we are expecting, the gain it should be 1, but here numerically you can say it is really close to 1. And then input resistance of the circuit, looking into this circuit. So, what we have, it is R in, you may recall from our earlier derivation, R in equals to R pi plus GM into r pi plus 1 into r naught, right, because this bias circuit we are assuming it is having ideal situation. So, its conductance is 0. So, this is r pi, it is 5.2 k plus gm into r pi, it is beta plus 1 into r naught, it is 10 to the power 5. So, again this is equals to, so this is 101 multiplied by 10 to the power 5. So, again this part it will be very small. So, we can directly approximate this by 101 into 10 to the power 5 ohms, or what we say it is 10.1 mega ohms. So, this is quite high. So, the input resistance, it is, as we said, it is very high, and this is approximately 1, this is tens of mega ohms. Now, coming to the output impedance. So, let me again clear it, and let you go for the output impedance. So, output impedance, it is looking at the output terminal, what we have, it is 1 by conductance at this point. So, we do have conductance here, conductance of the r pi, then r naught, and then also the gm part. So, the output resistance, it is 1 divided by all the conductances, namely gm, then due to r pi, and then due to r naught, right. Yeah. So, we do have the values here 1 by, so this gm, it is 1 by 52, 1 by 52 plus this r pi, it is 1 divided by 5.2 into 10 to the power 3 kilo, right, and then r naught, it is 10. So, that is 100 k 10 to the power 5, and again this is, it can be well approximated by this term. So, that gives us 52 ohms. So, that is the output impedance. Now, coming to the, so you can remember this one, for calculating the upper cutoff frequency. So, we will be coming back to that. Now, the input capacitance. So, we do have input capacitance C in. Looking into this circuit, it is what we said, it is C pi multiplied by a very small factor. So, what was that factor? It was r pi divided by, as you may recall, yeah. So, C pi into r pi multiplied by gm into r pi plus 1 into r naught plus r pi, and then C mu as is. So, again if you consider this is beta and this is very high. So, compared to that we can see that this is anyway small and this is also small. So, we can approximate that this is C mu and that is equal to 5 picofarad. So, we do have the output resistance. Looking into this circuit, it is 52 ohm, and then we do have the load capacitance here CL, it is 100 picofarad. So, we can say that the upper cutoff frequency now, so this is done. Now, the upper cutoff frequency, if I say that f u upper cutoff frequency, it is 1 by 2 pi R out or R O into C L. So, that is let me use different color, should say R O into C L. So, we do have 1 by 2 pi into 52 ohms into 10 picofarad. So, that is 10 to the power 10, right, and so this is 10 to the power minus 10. So, that comes to be 10 to the power 12, 10 to the power 10 divided by approximately, or say to be more precise, 104 into pi. So, that is 22 by 7. So, roughly you can see that approximately, if I say that this part it is 3 and then this is almost 100. So, that is 10 to the power, it is now this is we do have another 100. So, this is 10 to the power 8. So, we do have 100 divided by no. So, what we have here, it is 10 to the power 10 divided by 104 multiplied by 22 divided by 7. So, roughly this is 100 into rather multiplied by 7 divided by 22 megahertz. Yeah. So, it is more or less in the tens of megahertz. So, rather I should say no, I should say close to 30, approximately 30 megahertz. So, here it is 3, yeah, close to 30 megahertz. Right. So, that gives us some idea that even if say load capacitance it is 100 picofarad, the output the bandwidth of the circuit coming from the output node, it is quite big, and we are considering the source resistance is approximately 0. So, the Cin is not having much role to play, but even if I consider practical value of this source resistance, since Cin is small, then the corresponding bandwidth coming from the input pole will also be quite big. So, let us see in the next circuit that if we consider source resistance R s, which is say maybe having some practical value, then you can see what will be the corresponding impact. So, in the next slide, it is basically the same circuit, except here we are considering the R s different from 100K. So, if you see this circuit, if you analyze this circuit with the bias current of say 0.5 milliampere, and then if you try to analyze what will be the the operating point. So, we do have at the base, we do have the 6 volt out of this VBB, and then we do have the RS, and then base to emitter we do have a voltage drop. So, I should say I am just circling it to indicate that this is representing VBE on, and then we do have the bias current of 0.5 milliampere, and then here we do have the collector current, right. So, this collector current we may approximate that this is also equal to 0.5 milliampere. Now, to find the voltage here, what you have to do? So, we can say that I C it is approximately equal to 0.5 milliampere, or rather to be more precise it will be 0.5 multiplied by beta is 100 divided by beta plus 1, right. So, that is to be more precise. So, but then we can say that it can be well approximated by 0.5 milliampere, which gives us the base terminal current. It is 0.5 milliampere divided by beta. So, that is 100 again. So, this is equal to 5 microampere. Now, once we do have the 5 microampere flowing through this RS, obviously, then there will be finite drop here, since it is 100 kilo ohm resistance, that is quite large. So, we need to see what is the drop across on this resistance. So, the voltage drop across this RS equals to resistance is 10 to the power 5 and the current is 5 into 10 to the power minus 6. So, that is giving us a voltage drop of 0.5 volt. So, I should say, so this gives us the base voltage is equal to 6 minus 0.5. So, this is the drop across the resistance RS. So, that gives us 5.5 volt, and then the emitter voltage VE equals to the VB, which is 5.5 minus 0.6 VBE on. So, that gives us 4.9 volt. So, we do have the base voltage, we do have the emitter voltage, and collector voltage anyway it is 10 volt, and then base current is here, collector current is also approximately this one. So, that gives us the operating point. So, note that even though the voltage here it is different from significantly different from 6 volt bias here due to finite value of this source resistance, but since we do have the bias current here, it is ideal, quote and unquote ideal, of the same value of 0.5 milliampere. The collector current and base current hardly gets affected. Only thing is that the voltage here and voltage here, they are getting changed compared to the previous case. So, anyway, since the collector current is still remaining 0.5 milliampere. So, the small signal parameters on the other hand, it is remaining same as the previous one, namely the value of the GM. So, GM it is again it is 1 by 52 ampere per volt, then R pi it is 5.2 kilo ohm, and then R naught is equals to 10 to the power 5. So, that is 100 kilo ohm, right. So, since the small signal parameter it did not change. So, the voltage gain and then input impedance, output impedance, they will be remaining unchanged. In fact, if you see the output impedance, there will be a small change, we will see that, but the voltage gain no need to repeat here. So, again this will be very close to 1. Input impedance, looking into this circuit, it is remaining same. So, this will also be same. So, we will not be considering this calculation. So, if I consider this is the input impedance looking into the base, that is remaining unchanged, but then of course, due to the source resistance R s, the output impedance it will be different. So, that probably we can see what is the output impedance. Input capacitance again it will be approximately C mu. So, only thing is that let us try to see what is the corresponding output impedance of this circuit in presence of the source resistance R s. So, let me clear it. So, what we are going to do, we need to see what will be the output resistance. So, now you may recall that at this point, if we give a stimulus of say V x in the small signal equivalent circuit, then if we try to calculate what is the corresponding I x, and of course, this node it will be AC ground. So, we do have R s, and then this R s coming in series with R pi. If I try to sketch the small signal equivalent circuit here, and then here we do have the GM part, and then we do have the R naught part here. So, looking into the emitter here, and if we stimulate the circuit with the V x here, we will be having 3 current components. One is this, then another one is this one, which is GM into V x, and then the resistance here. So, you may recall that we do have the 3 conductances to contribute to I x. So, that gives us a hint that the output resistance it will be 1 divided by all the 3 conductances. One is GM, then 1 by R naught, and then 1 divided by R pi plus R s. Now, here we do have, and this is GM, it is 1 by 52, and then R naught it is 100 k. So, we do have 100 k here, 10 to the power 5, and then R pi plus R s. So, R s we are taking 100 k. So, this is 1 divided by 105.2 into 10 to the power 3. Again, compared to this term, the other terms we can drop. So, it is again it is coming 1 by 52, that means it is 52 ohms. So, even though we are connecting this R s since we do have the ideal current source and the small signal parameters remain the same. So, the performances of all the circuits it is remaining same. In fact, output the upper cutoff frequency also remains the same. Only thing is that whenever we are feeding the signal at this point, so since you are feeding the signal at this point, and then we do have the RS and also the input capacitance coming here, then we do have one more candidate to define the upper cutoff frequency, and that is, let me call FU 2, which is coming from RS and the C in. Of course, we have to consider the 2 pi part. And if you see in this case, the I should say that predominantly this again this since C in it is coming from C mu. So, we can say that this is 1 divided by 2 pi, then RS is 10 to the power 5, and then C in it is 5 into 10 to the power minus 12. So, that gives us 5 and 2 gives 10. So, this is 10 to the power 6, it becomes 10 to the power 6, and then we do have 10 to the power minus 12. So, that gives us 10 to the power 6 in the numerator divided by pi, and pi is approximately 3. So, we can say that this is approximately 1/3 megahertz. Whereas, the pole coming from the output node, if I call that is FU 1, which is coming from the output resistance 2 pi R O and then CL, and this one we have seen it was approximately 30, in fact around 28 or something like that. So, 30 megahertz. So, the upper cutoff frequency, of course, it will be defined by whichever is minimum. So, I should say that the upper cutoff frequency it is getting changed, but still it is remaining high, primarily due to the input capacitance here. It is actually coming from this C mu, and its value it is only 5 picofarad. Now, in case if the load capacitance, if it is directly connected at this point, namely if it is a 100 picofarad, obviously then this RS and then this CL, it would have created the upper cutoff frequency much lower than whatever the 1/3 megahertz you are getting here. Okay, so let me take a small break, and then we will come back with some more numerical examples.